Hello everyone and welcome back to ChatCraft. Last time I left you off with a really grand proposal. I am going to tell you how physicists manage to weigh the universe. At least I'm going to give you the broad picture of how they manage to do it. The exact details are complicated and I'm not 100% on them, so yeah. Basically, you can't just put the universe on some sort of massive scales and just read off the weight. It doesn't work, for obvious reasons. But of course, science has long ago stopped in many areas being able to do the literal thing. So, to weigh something, you put it on scales and read off the weight. Obviously, not the way we can go. But there's another way, and that's where we need the general relativity thing, which I talked about earlier. Because general relativity suggests that massive objects distort space and time. And the effect that you really want, or that you're using, is the effect that it distorts space. And general relativity is pretty much, it's not a guess, it's not a possibility, it's pretty much the explanation we have, which seems to be very good for the way the universe works. For example, the GPS systems, they account for relativistic effects, and they have to. If they didn't, the GPS systems wouldn't work. There's actually a really mild relativistic effect. Like, by mild I mean it's a very subtle effect, but basically, if you're higher up, time goes slower. That's actually something that has been observed as well. For example, if you're an astronaut and you're going off into space and you're traveling quite fast, and after 10 years you come back, it could be that 100 years have passed on Earth because you were going faster. Time has a different effect on you. It's like very fast things seeming shorter. That's not something that... It's a really bad choice of words, actually. They don't seem shorter. If something is going really fast by you, and I'm not talking 100 miles an hour, I'm talking meaningful speed relative to the speed of light, they are shorter. It's not just an illusion of being shorter. They are literally shorter. And so similarly, if you're moving really fast, time flows differently for you. And so, in the GPS systems, they had to account for those effects. Because if you're even if you go a meter above your current location, time will have a slightly slower effect on you. If you want to call that time travel, I guess you're welcome to, but it's a measurable effect, and it is large enough that if engineers had not accounted for that when developing the GPS systems, the GPS system would fail as soon as you changed your height. It would all break down and not work anymore. And the GPS system is actually one of I think the only engineering project ever that had to account for both special and general relativity to make it work, because it's such a precise system that these quite small at that scale differences, they matter. So, quite an interesting little thing. But one of the things, as I said, that general relativity implies is that you would expect a really massive object to be able to bend light around it like a lens. So, let's say we have a light source here at this torch, and we put a massive object here. We would, like in classic mechanics, you would expect if you stood right here, you would not see any light from that torch, because the light would go past. In general relativity, however, it tells you that if this object here is massive enough, the light from this torch can go and be diverted back here. So you could actually see basically past this object, which is a solid object, and see something that's behind it. And that effect, I think it's called gravitational lensing. And that effect is also observable in the universe. So people looked at a cluster of galaxies, which are the heaviest objects we pretty much know in the universe. They are not a single galaxy, they are multiple galaxies bunched together in a cluster, quite close to each other. And so we can see, if we take a picture of that galaxy, we can see gravitational lensing of a galaxy behind that cluster. So the light kind of goes around that cluster of galaxies, which in classical mechanics, in classical physics, obviously that's nonsense. How could light bend? It doesn't. But it does in those circumstances. And that was obviously a cool discovery. And you can use that. You can use that to work out how heavy the object is. So by looking at how much the cluster of galaxy bends the light of the galaxy behind it, you can tell how heavy the cluster of galaxies is, and more so, you can tell how the mass is distributed in that cluster. So you know precisely how heavy that cluster is and where the mass is in that cluster. And scientists did this, and the results were quite interesting. Because as it turns out, most of the mass in that cluster is not coming from the cluster, from the galaxies itself. Most of the mass, more than 90% I believe, comes from the empty space. So we knew empty space had a mass, but the number that had been calculated was grossly wrong. Or at least it seemed to be grossly wrong, and so other observations then confirmed that. Let me just look at my text. I'm on the second page now, but I think the second page has more stuff on it. Yeah, so 90% of the matter of the universe is made by some sort of stuff in between those galaxies. Stuff that doesn't reflect light, so we don't know what it is. We can't observe it. We can observe galaxies and stars because they give off light. Those, whatever that is, the stuff in between, didn't give off the light we need to make observations. And scientists also know that it cannot be just, I don't know, some non-shining object like a rock, for example. It can't just be rocks or planets that don't have suns or something, because they have a pretty clear idea of how much matter there can be in the universe, how much protons and how many protons and electrons and such. And those are pretty much all needed to make up the stuff that we can see, all the stuff that does shine. We need pretty much all this, the matter we know that we have to make the stuff that we can see. So the stuff that we can't see has to be made from something else, something that we previously didn't know. And scientists being what they are, they call it dark matter because it doesn't shine. They don't know what it is. They just call it dark matter. And so from all this, we do know how heavy the universe is, and as it turns out, we would expect it to be about 30% of the mass that we need to be a flat universe. As I said, the flat universe is kind of the middle option. In a way, it would be the most beautiful version. But as it turns out, the universe isn't quite heavy enough from those measurements. Which scientists weren't really happy with, because especially the theoretical physicists, they would prefer a flat universe. So, but we only had 30% of the mass. And, okay, obviously, based on some assumptions, instead, we can actually measure how the universe is curved. And I have to digress a little bit here. Well, I have to go into more detail here. What curvature means. Basically, if you take a triangle, you probably will have been told in school the sum of the angles inside a triangle is 180 degrees. Which is true in a Euclidean universe, in a Euclidean space. That's what I mean by Euclidean, basically. It's not quite the definition, but just for the purposes of this, take Euclidean to mean the sum of the angles in a triangle is 180 degrees. And you've been taught that in maths. In school, you've been told that's a truth. It is in a Euclidean space, but even in maths we have non-Euclidean geometry, which assumes, hey, let's assume it's not, and go with it. But leaving that aside, the universe doesn't have to be Euclidean. There's no reason it really has to be. We don't know if it is. Well, I'll get to that later. But the point is, for example, if you take a sphere, just for example, if you take a balloon or something, and if you draw a triangle on the surface of that balloon, if you make it large enough and you measure the angles, you can reach higher sums of angles than those 180 degrees. If I had a sphere in Minecraft, I'd show you, but I really don't. Nothing like it, in fact. But let's say there's a sphere here, and you take one corner of the triangle to be right there, one to be right on the top, and one to be right at the leftmost spot on that sphere. And you connect these, you get a sum of angles that's 270 degrees, because it has a right angle at each corner and still forms a triangle. So the surface of a sphere is kind of it's a closed surface. It's two-dimensional in itself. Well, not really. Examples really don't work that well, but on the surface of a sphere you can draw a triangle that does not have a sum of angles that's 180 degrees. And kind of the same thing would be true for the universe if it were a closed universe. If it were an open universe, you could have a triangle that has a sum that's much smaller than 180 degrees. You could get as close to 0 as you like, in fact. And an open universe is kind of like a saddle. Again, hard to demonstrate, but I guess I can kind of try and do that using these things. So ignore the one down here, that's just to build up the structure. And we need those. And those. So, oh dear, this is going to be a nightmare. Oh well, not really. This and kind of like this. So this is kind of the structure I'm going for, and this is roughly what you would expect a closed universe to look like. Not really. This is a three-dimensional representation. It doesn't really work, so don't imagine the universe to actually be like this. It's just to show the geometry, basically. And you could have one part of the triangle, one corner of the triangle here, and a straight line would be curving, basically. It would look curved to us, but it's straight in this geometry. And it would go here, and then again, straight line like this in the geometry, and straight line like this in the geometry. And you would have a sum of angles substantially less than 180 degrees. It's possible in different types of geometry, basically. And so that works in the universe as well. If you draw a triangle on your piece of paper, that's just not large enough. But if we're assuming we have a massive triangle, one that's large enough, like spanning half the cosmos, basically, and if we could somehow measure the angles in that triangle, then we could work out if the sum is 180 degrees or more or less, and from that deduce the curvature directly, instead of having to weigh the universe and kind of go with some slightly dodgy assumptions, maybe. So, how do you get a really big triangle? And that's where I kind of have to go into the details of what science did. Because we know when the Big Bang happened fairly precisely. It's like 13.7 billion years ago. The margin of error on that number is fairly small, so we can use that. And by the way, there is a version of Optifine out, but it still crashes occasionally, so I'm waiting for a stable release. Anyway, back to the important and interesting stuff. And we know that about 100,000 years ago, about 100,000 years after the Big Bang, the universe was about 3,000 degrees hot. At that temperature, matter isn't solid or gaseous, it becomes a plasma. If you want to know what a plasma is, look it up. It's not like a plasma cannon kind of thing. It's just a certain state of matter. And the important thing about that state of matter is it's impervious to certain radiation. That radiation doesn't go through it, but that radiation does certainly go through matter in solid state. It goes through matter if it's in a liquid state, in a gaseous state, but plasma it does not go through. And so what we would expect is that at that time, there's a bit of a wall, basically. It's not really a physical wall, but it's a wall that does not let certain parts of radiation through. In fact, it reflects certain radiation, because it's like a solid wall. If you look at a wall, what you see is the light bouncing off that wall and hitting your eye. And you would expect the same thing from that plasma wall. And because we know how old the universe is, we know that because we also know how fast it's expanding, we know how far away from us that wall is, or how far we would expect it to be. And the important bit about the 100,000 years is that 100,000 years after the Big Bang, anything that existed cannot have existed for more than 100,000 years. And what's so important about that is that if something hasn't existed for more than 100,000 years, it can only have a certain size before it stops being an object, basically. It's kind of hard to understand, I guess, but general relativity tells us that information cannot travel faster than the speed of light. So, if a clump of matter, or something that we would call a clump of matter, if that is bigger than 100,000 kilometers across, 100,000 light years across, sorry, not kilometers, light years. If a clump of matter is bigger, it's not aware in a way. Well, aware is really the wrong word, but there's no way for it to have become a clump, because gravity cannot have traveled from one end of it to the other. There just wasn't enough time. It's not old enough yet for gravity to have made that way. So we know that 100,000 years after the beginning of the universe, after the Big Bang, there can't have been anything bigger than 100,000 light year across. It's just wouldn't be possible, because it couldn't be one object, because gravity wouldn't have worked yet. It just wouldn't have made it all the way across. So, if the Big Bang indeed did happen, we expect, well, we're assuming the Big Bang happened, basically, from other evidence. And from that we deduce that the biggest objects that there are to be found at this wall of plasma, which is impervious to radiation. The biggest object on that wall would be roughly 100,000 light years across. Well, pretty precisely 100,000. It's not really an estimation. It's 100,000 basically. So that's basically what's giving us the triangle. We know how far away the wall is, because we know how old the universe is, how fast it's expanding. We know how far away that wall of plasma is. And we know how wide across objects on that wall are, because we know an upper limit, so if we take the biggest ones, that will give us a good idea. And so, in essence, that's the triangle we kind of... it's big enough so we can use it. Because if you know how long the three sides of a triangle are, you know the triangle, basically. And so, doing all the calculations, in a flat universe, the angle would have to be 1 degree at which we see those objects, the largest objects that we see in the cosmic background radiation, which and that radiation does exist in really old televisions, back in the days when at night television stations would shut down and there would be static. Part of that static would come from the background radiation from the Big Bang. And the point of the matter is, scientists have been able to actually look at that particular wall of plasma by looking at how the cosmic background radiation looks, because all other matter is pretty much transparent to that radiation. It just goes straight through stars, straight through a galaxy, straight through empty space, and we can see how it is, and we see clumps on that background radiation. And depending on how large these seem to us, because we know how large they must be, they cannot be larger than 100,000 light years across, because otherwise they couldn't be clumps, as I explained. So we know how large they are. And depending on how large they appear to us, we know which curvature the universe has. If they seem smaller to us than they are, then the universe would be open. If they seem larger, it would be closed. And from the current data, we deduce that, in fact, they look exactly as big as they would be in a flat universe. So, within, I think the experimental error on that is roughly 1%, we expect the universe to be flat. It's pretty much flat. So, if you've been listening carefully, you will remember. Earlier we had the weight of the universe worked out, and that told us that the universe wasn't flat. It told us that it was open. We only had 30% of the matter we needed. And I also told you that a flat universe, the expansion would slow down. We know the expansion is accelerating. So, we then go further. We have worked out the universe as flat within 1% experimental error, so something with the 30% of the mass needed, something must be wrong with that. So you look at how much the universe is accelerating, the expansion, and you sort of calculate that there is obviously some sort of repulsive force in addition to the initial blast of the explosion, basically. Something else to counteract gravity to make the universe accelerate faster. The expansion to accelerate, basically. Sorry. So you just go with it. You just say, okay, something has to do this. There has to be some sort of effect which increases the speed of this expansion. Some repulsive force. And then you, as in, not as in disgusting, but as in it repels matter from each other, basically. And you don't know what it is. You just go with it and say, okay, let's just say it's there. How big would it have to be? And it's in empty space, and we know how much that weighs, and so you just work out how much energy would we have to put into that empty space to make the universe expand at the rate that it is expanding at. And the amount of energy corresponds very precisely to the amount of energy that is still needed. As I told you, the matter we have measured only makes up about 30%. The other 70% is pretty much exactly what is needed to get the universe to be flat. And that's obviously a very beautiful discovery, because it confirms and it explains everything. It explains why the universe is accelerating rather than slowing down, and explains why it's flat despite there not technically being enough mass. And we have no idea what that energy is, where it comes from, why it is there. We don't know what dark matter is either. No idea. We know it's some sort of unknown particle, because it can't be neutrons or electrons or protons, because we've used all those up. So that all in all basically tells us we live in a flat universe. And it also tells us that all the matter you see, like not only this planet, everything we see, all the other stars, all the other galaxies, makes up about 4% of the universe. The other 96%, we have no idea what the hell it is. It's something, we know it's there, but what it is, it's guesswork. So that's the topic covered. I think that's a massively interesting topic. It tells us just how much science can do from looking at the stars. Just how much we can deduce from that without being there, without having any way of going there, it's not likely we're ever going to go to another galaxy. And certainly we're never going to see that wall of plasma. But we see what it does. We see the effects of it. And they work out. The theory stands up and it holds, and it really explains everything that we've observed. And in a way, it also tells us rather a lot about the future of the universe. As I said, we would expect the universe to keep expanding forever because of that dark energy. If we learn more about the nature of it, maybe it'll turn out that we really don't expect it to go on forever. Maybe because of the nature of dark matter, things will change at some point. We don't know. What we do know, though, is that at this point in time, it's a rather special point. Like, not a precise point, but this framework of time we're currently living in is rather special in the sense that if another civilization would emerge in our solar system billions of years later, after us, because we know rather precisely when our sun is going to fail and burn up, and at least Earth is not going to be inhabitable anymore, and at current estimates it's not likely we're going to be gone elsewhere by then, but a much later civilization could arise. And this civilization, if they have scientists, they could come to the same conclusions about quantum dynamics, about gravity, about biology, chemistry, all that. They could deduce these same things about their world than we have. But because it's so much at a later stage and the expansion of the universe has been going on, they will no longer be able to detect the background radiation. They will not be able to detect other galaxies. They would see their own galaxy. They would still see stars in the sky, but they would not see other galaxies. So their image of their world would be a single galaxy in a static universe that's forever and eternal. And they would have no data to prove that wrong. So, in a rather sad way, or maybe not sad, but in that way, their science could never work out their universe correctly. They would have wrong results without ever being able to get the right results. Which I guess could be a little depressing, but as I've taken a lot of this information from a certain lecture, and if you watch that, you will recognize a lot of the things I've said. I'll remember to link it. Maybe if I don't, remind me and I'll link it. It's interesting. And the guy who held the talk, he is a cosmologist, so he knows about this. A lot of things I've had to explain probably weren't explained completely correct. But yeah, we do live in a special time in the sense that we are able to tell we live in a special time. So there's another thing that you might encounter this argument from certain people, because from all this cosmology, and the first bit is actually true. So we deduce that if the ratio of matter to dark energy, if that had been largely different, like a lot different, life could not have formed. Galaxies could not have formed because the repulsive force would have been too great or too small. So either the universe would have contracted way sooner, or because the repulsive force is stronger, galaxies could never have clustered together. Everything would have just blown apart. And so this is true. And certain religious people will tell you that that's evidence that the world has been designed, because the constants and the values have all been made so perfectly to sustain life. And at first thought, that can be a difficult argument to refute, because it seems so true. The point, if you want to refute that, the point is, we live in a universe. Obviously, a universe in which someone lives has to be a universe that supports life. So we would expect the universe we live in to actually be one that supports life. It's something called the anthropic principle. It's kind of a philosophical argument, but it doesn't prove that the universe was kind of finely tuned for us. Obviously, if the universe had been different, we can live in it. So yes, when we observe the universe, we expect to see a universe that supports life, because it does support life. And that kind of makes that argument completely pointless. Well, it's an argument that others have said is difficult to refute, but I don't see it. If there's an error in my reasoning, of course, point it out, but it seems to me to be obvious that, yes, well, whatever observation I make about the universe, I expect that the universe I observe to be able to sustain life. Surely that has to be the case, because it clearly does sustain life. Unless we go back to the matrix argument. So anyway, I found that a massively fascinating bit of science. As I said, if I remember to link that lecture, feel free to watch it. I think the guy giving that lecture, he actually, one thing I wanted to check. Wait, no, that doesn't work. That does. Okay, I've got my skin back. Last time I played, I was Steve. The guy who holds the lecture is better at explaining things, so if you were unhappy with my explanation, watch his, it's better. And yeah, I guess I'll see you next time. Bye bye.